Okay, so now let's move on to further topics such as nomenclature, right? So for the nomenclature, what do we mean by that? So we mean the names, right? So because eventually we're going to go ahead and then name our alkanes in some way, right? So what we need to do is be aware that there is going to be some amount of memorization, right? So for example, you can see the chart of various um, alkanes, which consist of different number of carbon atoms in their chain, right? So what people decided to do is take a look at the straight chain alkanes from one carbon atom to 10 carbon atoms and give them the specific names because it turned out it was easier to kind of like remember those given names and then name derivatives based on those compounds, right? So what we're gonna take a look at is like different numbers of carbons in the chain of an alkane, right? And then we're going to have like a specific names, right? So basically, you have the what's it called? You have the carbons. Um, different number of carbons in a chain, so from 1 to 10, right? So that's what we need to remember. So if you have just like one carbon in a chain, that's going to be for alkanes specifically, we're going to have the compound like that, so which is going to be methane, right? So that's going to be our methane compound. So if you have 10 carbons in a chain, that's going to be called decane, right? So that will all have specific names according to the table. So that table is supposed to be memorized. So then if you look at like further items peculiar to the nomenclature, so that's going to be about the roots, right? So if you take a look at, let's say, butane, right? So butane, according to our table of alkanes, is supposed to look like that, right? So that's a butane. So it has 4 carbons connected in a straight fashion to one another, and it will have the respective number of hydrogens like that, right? So this is going to be our butane molecule. So what's going to be also peculiar is that they will have the roots, right? So such as here we'll have the root but, right? So if the name of this alkene is butane, right, we need to pay attention to the fact that it has the root, right, which is going to be but. So this root is important. Why? Because it will be used to name other compounds that will also have 4 carbons in the chain, but they might as well be not alkanes necessarily. They might be alkenes, alkynes, and so on. But typically, we are going to deal with the notion of the root when we name organic compounds, right? So then we'll have here also the suffix, right, which will signify what kind of compound we have, right? Because depending on the kind of the suffix, we are going to identify our compounds either as like alkanes or alkenes or alkynes, to name a few examples. Okay, so then what else? Let's take a look at now at further topics here, which is going to be about nomenclature rules. So in this case, we are going to take a look at some. Let's take a look at substituents first, and then we'll put them together into some sort of compound, which we are trying to name, right? So if you look at the tables that follow the table of various alkanes, right? So with the nomenclature of like very fundamental alkanes, you will see that turns out there exist various types of alkyl substituents which can be attached to various chains in alkanes, for example, right? So, and those substituents were kind of identified because they happen to be present in many various organic compounds, right? So people saw some kind of like repetitive elements, so to speak, repetitive features, and I decided to say, well, so if we have these particular combinations of XYZ atoms, we will call it a particular name. So that's what a substituent is about. So for example, you will have various substituents varying from methyl to like isopropyl and sec-butyl, right? So essentially, if we take a look at some substituent example, so how can we wrap our minds around it, right? So let's take a look at the methyl, right? So methyl is going to be looking like this. It's going to be CH3, right? So that's the structure of the substituent called methyl. So CH3. Essentially, so this squiggly line means that this CH3 piece will be attached to something else. Maybe it's going to be, let's say, 5-carbon chain, right? Entirely possible. Maybe it's going to be just hydrogen, right? So, but the point is that the substituent will have this kind of like free valence that stems from typically the carbon, if we look at the alkyl substituents in this case, right? So this is going to be the methyl, right? So if you look at methane, methane looked like that. It was nothing more than CH3 with an H, right? So you see, if this compound in the circle is called methane, this will be nothing more than methyl, right? So the major change here is that we basically removed this hydrogen from the methane and we went from CH4 to CH3. That's how we make a substituent, right? So if you have if you have a look at some other examples, such as maybe ethyl, right? So what is ethyl? So ethyl is supposed to look like that, right? So CH3 attached. So this is a carbon-carbon single bond attached to CH2, right? And then CH2 has this free valence, right? So free valence stems from the carbon, not from the hydrogen, right? So it's just the conventional way to show this drawing, right, in the condensed fashion. So ethyl came, guess what? From where? From ethane. So ethane used to be CH3, CH2, and another H was here, right? CH3, CH3, basically. That's what ethane was. But now, from ethane, somehow, chemically, we removed the hydrogen and we went from C2H6 to C2H5. So now we have the ethyl as our substituent, right? So then again, substituents, just like functional groups, are characterized by a specific arrangement and sequencing of the atoms and bonds. So, and then they are named in the respective fashion, right? So again, the piece of advice number one here is to memorize the names and how substituents look like, right? So then moving on, we can also have some kind of like non-alkyl substituents, right? Which are not derived from alkanes, but which can be represented by standalone atoms, such as, for example, fluorine, right? So that's going to be like a typical substituent. Maybe you'll have the chlorine. So basically here, so let's say chlorine, right? So this is going to be a substituent named chloro. So what does it mean? So this substituent can be attached to some sort of carbon chain, right? And then that way you are going to have the so-called substituted alkane, for example. If we look at the attachment of this chlorine atom to some sort of carbon chain, let's show it this way. Here we go. That's your practice of the condensed formula, right? And then here, you look at this carbon, right? So this carbon is attached to one carbon, another carbon, right? So it's attached to the chlorine, and then also it has to have 4 bonds total, right? So what's not shown is the hydrogen, right? The hydrogen and carbons are implied. So here we must have only one H. That's the only possibility. It cannot have just 3 bonds, right? Or 5 bonds all of a sudden. It must be tetravalent, right? By the way. But if you look at the original carbon or hydrocarbon, it used to be 1, 2, 3, 4, 5. 5 carbons in a straight chain, right? So only carbons and H's. But now, so that piece used to be CH2. However, we removed one H and we switched it to chlorine, right? So now we have not CH2 here, but CH chlorine. So we have this substituted alkane because we have a substituent here, which is chlorine. And also we can say that one of the hydrogens in this alkene was substituted to a chlorine substituent, right? So, or chloro, more specifically, substituent. So we have like a wide range of substituents, which again are characterized by their specific combination of atoms attached to one another, which again is a good thing to memorize. Right, so now we're going to go ahead and then take a look at some examples of nomenclature, right? And then how we can name organic compounds, right? So let's take a look at this. So naming of alkanes can be uh, explained using examples, right? So let's take a look at a relatively big alkane molecule and try to name it, right? So you have all the rules in front of you, like in the book and on the slides, but I think examples would be very good to have. So let's take a look. So for example, we're going to have in one of our slides, we have this relatively big organic molecule, right? So which goes like that. So let's say we are going to have a carbon chain that consists of 7 carbons. So here we have CH3, then CH2, CH, CH again. So then we have another CH, so it's going to be 4 CH pieces in a row. So 1, 2, 6, 2, 4, 6, and 7. Okay, so 7 carbons like that, right? So then we have, so here is going to be our 7 carbons in a chain. So then we're going to start branching of this chain, and then we're going to attach various substituents to that chain, right? So this is going to be just kind of like a very good example of what an alkane might look like, right? So it contains a lot of carbon atoms, and then it has a relatively complicated structure. It's not just like a straight chain of, let's say, like 6 carbons, right? So we have a lot more carbons, and we have the branches here, which stem off the main chain in your alkane example molecule. So here we have more kind of building blocks, right? And we have something like that, and then we have another one, right? So let's say what's going to happen here, right? So first of all, according to our nomenclature rules, we are going to identify the longest chain, right? So we can go ahead and then take a look at various chains, right? So the chain is going to be just the connection of the various of several carbon atoms in a sequence, right? And then it doesn't necessarily have to appear straight. It can be going down, can be going up, right? So there could be some kind of like twists and turns, so to speak, in the connectivity, right? But it should be a consecutive chain of carbon atoms, right? For example, if you look at this one, right? So it is a consecutive chain of 3 carbons, which seems to be kind of relatively short, but it's still a chain of carbons, right? So this is also 1, 2, 3, 4, also a chain of carbons consecutively arranged, right? And linked to one another. So this chain here contains how many? 1, 2, 3, 4, 5, 6, 7. That seems to be so far the longest chain. This chain contains 1, 2, 3, 4, 5, 6. 6 not as long as 7, right? So it looks like 7 is the best, right? So now we're going to take a look at the substituents here and also the numbering of the chain, right? So we're going to number the chain from the end. So we can go either left to right or right to left. It doesn't matter. What matters is that we are going to start numbering the chain from the end closest to the branching point, right? So here, if we start numbering from right to left, we're going to be like 1, 2, right? And then this end is quite close to the branching, right? So it's already kind of like the branching starts at the second carbon. If we start numbering from this end, we are going to see that 1, 2, 3. Then the branching only starts from carbon number 3. So if we start numbering from this end will be farther from the branching point, which is not good for us, right? So we need to start numbering the chain from the end, which is closer to the branching point, which is going to be the right end in this case, right? So that's where we are going to start numbering the chain. And then we are going to just put the numbers down. 1, 2, 3, 4, 5, 6, 7. Okay, great. So now let's take a look at the substituents. We can circle them, and then it's going to be substituents like that. One, we have another one here. So these are our familiar already substituents from our previous information, right? We have 4 substituents here. So another caveat that you might be asking about is that what about the other chain, right? That contains also 7 carbons. So here we have it, right? 1, 2, 3, 4, 5, 6, 7. It's also a straight chain, right? So it's a chain of consecutively connected 7 carbons. But why don't we choose that chain, right? So that's what we have in the other like possibility, right? So then the argument here it will be in the following, right? So if you choose, let's say, this horizontal chain of 7 carbons as your main chain, you are going to identify that 4 substituents are attached to that chain. That's one of our rules, right? We need to have the longest chain, right? So with the greatest number of side chains. If we take a look at this chain, right, which is an alternative, right, to our naming, to our search for the longest chain, it also has 7 carbons, right? So, but it will only contain, look at this, 1, 2, and this is going to be the third substituent right here, right? So this like big substituent of 4 carbons. So this alternative chain will contain only 1, 2, and 3. So I'm trying to circle this 3 substituents, which is not going to be good for us because 3 is less than 4 substituents, and then we're going to find the longest chain with the greatest number of substituents, right? So that's just like one of those like rules that we will need to pay attention to. So then what else? So then we're going to name it, right? So we have our substituents identified, right? So what's that in the circle? This is a methyl, this is also a methyl, and this is another methyl. In this bigger circle, we'll have a different combination of carbons and hydrogens, right, in this substituent, which is going to be known as a propyl, right? So we have 3 methyls and we have 1 propyl in our organic compound, right? So let's start naming it, right? So we are going to put down the root corresponding to the number in the longest chain, right? So the root will be corresponding to the 7 carbons, right, which is going to be hept, right, hept. Since it is an alkane, we're going to use the suffix "ane" to signify that we have the alkane. And now we'll show our substituents on the left side to the word heptane, right? So let's get to that, right? So what do we have here? We know that we are going to arrange substituents alphabetically, right? So we have methyl and propyl. So M is first, then P, right? So somewhere we are going to have methyl, which is going to precede the word propyl, right? So propyl. So these are our substituents in this organic compound, alkane. Right. So now let's take a look at how, like, where are those substituents located, right? So you see here that we have 3 identical groups, right? So such as 3 methyls attached to the carbons 2, 3, and 5. So let's just show that those methyls are attached to the carbons 2, 3, and 5 by putting down the numbers 2, 3, and 5 before the word methyl, right? So on carbons 2, 3, and 5, we'll have only methyls, right? But total we'll have 3 methyls, right? So that's why we're going to use the prefix tri before methyl. 2, 3, 5 dash trimethyl, one word. And then this will signify that total three methyls will be distributed between carbons 2, 3, and 5. Or you can, in other words, say to yourself that carbon 2 methyl, carbon 3 methyl, and carbon 5 another methyl, right? So that's what this combination of words and numbers will mean, right? So then propyl is going to be a little bit easier, right? We have only one propyl attached to carbon number 4. So consequently, by the same token, just like here, we are going to put 4 before the name of the substituent, and it's going to be 4-propyl, right? So total we have 2, 3, 5 trimethyl, so all checked, dash. 4 dash propyl, checked, right? And then it's all going to be kind of like housed on the molecule of heptane. So it's going to be basically like a hugely substantially substituted heptane molecule, nothing more, right? So you basically started with a heptane, and then somehow chemically you remove, let's say, H, and you switch those respective hydrogens to the respective substituents that you can see in front of you, right? So that's why you have this particular name for the compound.